We're going to leave our recursive relations and definitions a little bit. We'll return to them very shortly, but we have to do one chapter on counting, because we need these ways of being able to count certain things. Okay, so these are counting principles, and there's one section 6.3 on permutations and combinations. I'm not going to say much about them. It's an optional reading, but it might really be helpful to know this, because once in a while you kind of run into such a thing. Okay, and that is about the problem there is choosing, let's say, 5 people out of 12, and there are two different possibilities. You can either choose 5 people out of 12 in which you want to order these people. The order in which you choose them is important, or you don't. It doesn't matter which one you pick first, as long as you have 5 of them. And so this is the difference between permutations, where the order matters, and combinations. So go look at that, because it might be useful in what comes here. But this is somehow perhaps a little bit more elementary, but it's not so simple. Okay, so you're really going to have to think hard about this, especially when the problems get more complicated. And basically, there are 2 counting principles, that 2 major principles. There will be more, but there's a big dividing line, and this is what we call the so-called sum rule, and there's also the called product rule. Now, before I work on each, let's look at an example. Okay, so let's suppose you say you're going to a restaurant and you want to eat something, but you're not that hungry, so you decide that you are going to do 2 different choices. So I'm going to choose either an appetizer or a dessert. Okay, and so here it's, you could say, is it an exclusive or not? Well, appetizers, and desserts are desserts, so it doesn't really matter that much. So suppose, here is the menu. So here's a menu, just an excerpt of the menu. Here are the appetizers. Under the appetizers I have, say, Caesar salad. And there is also calamares that I like. Squid. And there is also, let's say, nachos, which is not healthy, but it's very good. And what else? Mozzarella sticks. Okay, let's say there might be a bit more, but let's stop here. And then as it comes to desserts, what we have here, we have, let's say, chocolate mousse, which is my favorite, chocolate mousse. Or there is cream cheesecake. Or there is fruits, let's say assorted fruits, and what else? And ice cream. Okay, that's ice cream. And let's say there's only one flavor, that we don't have to worry about it. And let's put one more, and there's also sorbet. Okay, so I choose either appetizer or dessert. So how many possibilities what are the many scenarios? Suppose these are happening in different circumstances, I have different tastes or different flavors. So what are the possible choices? How many different orders can I give? Okay, so what do you think? Let's think about it. Well, I have to take either an appetizer, which gives me 4 choices, or a dessert, which is 5 choices. So all in total, how many choices, how many different orders? So the number of possible orders. So this is always, discounting is always about possible choices, right? Possible ways of doing things, possible scenarios, different ways of formulating this. Possible orders, how many are there? Well, there are 4 appetizers and there are 5 desserts. So in total, I have 9 different choices. Okay? So what is now, this is a sum, so this is probably the sum rule, right? What is the product rule now? Well, look at the sum thing. I'm going for dinner again the next day to the same restaurant. I liked it very much. But this time I'm a little bit more hungry. So I'm saying I'm going to skip the entree, but I'm going to take an appetizer and dessert. So order 1 appetizer and 1 dessert. So what has changed now? Well, the change is now that I'm not taking 1 thing, but 2 things. And I'm taking 1 from the appetizers and 1 from the desserts. So how many different choices are there? Well, we could try to list them, okay? So let's say, I'm not going to list them all, but let's say, my first thing is I could take a Caesar salad, and then I could go with either chocolate mousse, cream cheesecake, fruits, ice cream, or sorbet. So just taking Caesar salad gives me already 5 different orders. There are 5 orders that contain Caesar salad. Now, what about calamares? Well, the same thing, right? The calamares I can combine with each of these. Nothing excludes these. Whatever I do here is, whatever choice I make here is independent of the choices here. Okay, so this is important principle. That is that all our choices are independent. And dependence is much harder, and this is more something you learn in statistics and so on. So, okay. So what is this now? Let's think about it. So for the first of all these choices, there are 5 other combinations. With this one, there are also 5. For this one, also 5, and this one, also 5. So 5 plus 5 plus 5 plus 5, 4 times 5, the product rule. Okay? So let's write it down. So the number of orders, the number of possible orders is now 4 times 5, so that's 20. That's much more. Okay? Product, of course, always gives, in general, a bigger number. And so this is the difference, okay? So one thing to think about it is, in the sum rule, we are choosing 1 thing. In the product rule, we are choosing 2 things, in the simple scenario, okay? And that's one of the differences. Another difference is this here, or, right? It's either or that I'm taking, whereas here I should have spelled it out, but you know this is and, right? So this is another way of telling them apart. I'm not saying that it always is that what it makes the difference, but it very often is, okay? So this is often an or situation, and this is an and situation. In an or situation, you pick 1 thing, right? Because you have to pick 1 or the other, or something, or here 4 choices or 5 choices. In an and situation, you pick 2 things. And in the simple setup. Okay, so let's look at each of these examples of each of these. So let's talk about, let's see, the first thing I want to do is, okay, so very often we're going to talk about bit strings, so let me tell you what this is. So a bit string is a combination of 1s and 0s. So it's a binary, or sometimes also a binary number. So it's another way of saying a bit string. So 1s and 0s, okay? And the length of a bit string is the number of bits, okay? The number of ones, the number of digits, if you want, 1s or 0s, okay? That's clear. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9. So the length here is 9. Length is 9. So you could ask, how many bit strings are there of length 9? How many bit strings of length 9 are there? Now, okay, I say binary number, it's not exactly correct, because a binary number is not supposed to start with a 0. And in bit string, it can start with 0. So perhaps I should not say that, but just to have an idea what I mean, right? Okay, so this is a valid bit string. It's not a valid binary number, because a number is not supposed to start with 0, but it is a valid bit string. Okay, so another one, this is, let's make one of length 9. This is another one. Okay, how many are there? Well, we are now in the product rule, because why? Because very often the way to do this is, think of this as a process. Okay, and you're producing this this bit string, and there are many sub processes that you have to do. Namely, you have these 9 positions, 6, 7, 8, 9, and each of them has to be filled in with something. So you have 9 different things you have to do. So there are 9 procedures, and every procedure, how many ways can you carry that out? Well, you can put in the first spot either a 0 or 1. So it's either 0 or 1. So the number here is 2 possibilities. to choose just this one bit. The same here, we have two possibilities, so also 2 here. Now, whatever I choose here has nothing to do with what I choose there, right? So whatever, sorry, I should point, whatever I choose here has nothing to do with what I choose here. I can choose a 0 here and a 1 here. The choices are independent. I want to point it out sometimes to you. So that means that if I would think about just length 2 here, what should I do? Add or multiply? Luckily, it doesn't make a difference, right? But what is the right thing to do? Multiply, right? Because I'm constructing 2 things now. I'm constructing 2 bits, so that's why it's 2 times 2. So I have to times it here. Now, if I make a 3rd bit, again there are 2 possibilities, so I have to multiply again. Okay, there are 2 possibilities here, 2 here, 2 there, and they are independent, and we are constructing. And in this case, a 9 tuple of zeros and ones, a bit string. So in total, okay, so if we go on, so times 2, so this is 2 to the power 9. Okay, that's the number of bit strings. That's not so surprising, right, that it's that number. Okay, so bit strings we're going to use quite a lot, so it's good to know all this. So for instance, how many functions are there? Are there from A to B, where A has, so a function, remember, is kind of an input. Suppose here we have M, so the cardinality of A is M, and the cardinality of B is N. Okay, so the question is how many functions? What is a function? A function is an assignment of each element in A. Let's call these elements in A, there are M of them, let's call them A1, A2, ... AM. Right, but we have done this in our pseudocodes and everything, like we list them basically. We don't know what they are, but this is our thing. We named them for the moment this way. And what is now a function? Well, a function says each of these has to be mapped to something here. Now, do these map? When we talk about a function, there is no restriction on where it goes to. As long as it's an element of B, it's fine. You can map all these things all to the same element in B, or all different elements in B, it doesn't matter. Okay, that's what a function is. So how many choices do I have here? So the number of choices, just to send out A1, well, it's these n elements. So I have n choices here. And how many choices have I for this one? N. And again, a function, as I said, has no restrictions. I can send it to the same, I can repurpose these elements. Okay, so this means that this first choice of what A1 goes to is completely independent of what A2 goes to. Okay, so again we have a number n choices, and so therefore if we would just have 2 elements, how many possibilities? There would be n times n already. Okay, and now we of course we have m many, so we have n possible choices, n choices here. So the whole thing would be n times n times n. How many times? N to the power m. Okay, so you see that this makes really quite big, right? Even if you start with 3 elements here, let's say if m is 3 and b is 7, has 7 elements, this is already a quite huge number. It's 3 to the power 7. Okay, that is already, well, 5-6 digits number. So this can blow up quite a lot. Okay. Now let's look at a little bit more complicated thing. So far what we had was the processes. So it is a procedure. We building a string or we constructing a function, and each operation, each sub procedure, each way of doing this was basically uniform, right? In the first case I had to choose 0 once, and it's every single time I was choosing 0 and 1s. Okay. In the second time, I had to choose. In the second one, you had to choose n elements, but it was always the same n elements that I could choose from. But here's, for instance, a different. Area codes in North America. Okay, where does it go? Sorry, not area codes. I mean telephone codes. I call it area codes. I'm saying it wrong. So in North America, because it includes also Canada, and a telephone number looks as follows. It's digits, right? And so the digits, we have 1, 0, 2, all the way up to 9. But you know that certain combinations cannot happen. For instance, an area code, let me make sure, because there are differences, things have changed since, yeah. An area code cannot start with 0 or 1. These are special area codes. So we in order, so how does a telephone number look like? 334, right? But this is the format that this is officially the format that looks like this. I'm going to write it down first and then tell you what I mean with this. So any telephone number is of this form where X is any of these digits. And what is N? N is any of these digits, not 0 or 1s. So neither this area code nor this so-called or what is it called? It's called the station code. The station code can start with a 0 or a 1. Okay, that is just to have special numbers, keep them so that people can recognize immediately what kind of number you're dealing with here. So let's count how many possible telephone numbers are there, and there's no other restriction. So what is this right now? Okay, again, there's a procedure. We're producing this, and we're gonna have to make choices. We're gonna do this 10 times, but let's see how many choices, the number of choices here. Since the first N, I can only choose between 2, 3, 4, 5, 6, 8, 7, 8, 9. There are only 8 choices. Okay. This next digit, I have more choices because I can also include 0 and 1. So I'm going to have 10 choices here. Also 10 choices. 8, 10, 10, 10, 10, 10, and 10. So imagine building this up. You start with choosing the first number, but you have to choose a number from 2 to up to 9. So you have 8 possibilities. Once you do this, you move to the next number. Now you have 10 possibilities. So this is what this means. And so in other words, we have to multiply all these numbers. So let's see, that is 8 times 8, that's 64 times 1, 2, 3, 4, 5, 6, 7, 8. 10 to the 8. 10 to the 8 is 100 million. So it's quite a lot. This is 6,400,000,000 numbers. Sounds a lot, but we're actually kind of running out of it. So they're going to have to at some point to do something. Because a lot of numbers sometimes are used, not really used, but people have claimed them and stuff like that. Yeah. Okay. So you see, here we have a non-uniform, right? There's difference. This is exactly what happened in our first example of the product rule, where we had a different number of appetizers as desserts. Okay, just keep that in mind. So another way of thinking of this, as I said, is what is set theoretically. So we're producing, let's say, a string. From the first set, we can choose the first element from the first set, the second element from the second set. So for instance, this would be, in my case, A1 here, and this would be A2, for instance, right? And so what represents now all the possibilities, that is an element from all possibilities of an order of one appetizer and one dessert. It consists of these guys, and it's a pair consisting where the first element comes from here and the second element comes from there. Now we have a very good set theoretic notation for that. That is this notation, the Cartesian product. So I'll go look this up in the previous chapter that we studied in discrete math 1. So the Cartesian product is exactly all the pairs. Where the first pair, so these are pairs, A1, A2 elements, where A1 is an element from A1 and A2, little a2 is an element from capital A2. Okay? And so what the product rule says is that we have the product of the cardinalities. Okay? Yeah, so sometimes I use this sign, I use this sign here to denote the number of elements, and sometimes I use this sign. Sorry about that. It's a habit of mine to use both because it's really almost interchangeably used everywhere. Okay. So let's go now back perhaps to the sum rule. Okay. So it important now is going to be to notice the differences when a question is asked. Is so when are we doing? In which situation are we? So for instance. So suppose you have to, there are 3 quizzes, okay? Oops. No, so sorry, I said it wrong. So there is a quiz, and on the quiz there are 3 questions, okay? And you can, there's a question, let's say, there's a question on, let's make it a calculus quiz, okay? There's a question on derivatives, there's a question on integration, and there's a question on series. If you have not taken Calc 1 or 2, then you don't know exactly what I'm talking about, but it doesn't really matter, okay? So the professor has made this, this quiz, and it says, okay, I'm gonna ask you to do 1 derivative question, 1 integral question, and 1 series question. And so there are, how many derivative questions? There are 3 different derivatives that he has given, possible derivatives. He has given 2 integrals, and there are 4 series. Okay? And so 3 questions, choose 1 of each. Okay, so this is again a product rule, right? Because let's see, what are my options here? I have to choose a derivative, so there are 3 possibilities. I have to choose an integral, that is 2 possibilities, and I have to choose a series, is 4 possibilities. So in total, there will be 24 different possible choices for this quiz. Okay? Okay, but students were complaining, Professor, this is way too much, we cannot do this, we don't have the time to do this, this is way too much work. And then I says, okay, I changed my mind. You can choose 1 question, and you can choose it from the derivatives, you can choose it from integrals, or you can choose it from series. So now, so this is the first question, right? So the second one is now, choose 1 question. Okay. So what is now the number of possibilities? Well, now I have 3 derivatives that I can choose, or 2 integrals, or 4 series. So it is 3 plus 2 plus 4 is the number of possibilities. So each time what I'm calculating is the number of possibilities, the number of different type of quizzes that could be made that way. So now there are 9 possibilities. You see the difference between the end, where you have here, because you had 3 different choices you had to make, so you end up with 3 questions. Here you had 1 choice to make within 3 categories. Okay, so there was an or here. So if we represent this again with A1, A2, A3, so again, in the first case, the total all the possible questions are listed as a set, are exactly given by this Cartesian product. And the cardinality of this product we have seen is the product of the cardinalities. Okay, cardinality of a set, remember, is just the size of the set, the number of elements in the set. What is happening here? Well, what is the corresponding set that corresponds to choose 1 question? That is a union, right? Remember, the union means you take, it's putting all the possibilities together, okay? And so what this sum rule says, it is now the sum of these sets. But I have to, a little proviso here, we'll come back to it in a moment, is these 3 sets, A1, A2, A3, were different collections, right? They had nothing in common, so they were disjoint. So I should put this here that these AI are disjoint. Remember, disjoint sets mean they don't have anything in common. This is important. We'll come back to that. I don't want to do more on the sum rule. I want to now combine them. This is where it gets tricky, right? So okay, so let's say you guys are way too young for this, but most of you, I'm assuming, but I grew up with one of the very first programming languages was called BASIC. And it was really basic, it was horrible, but okay. And in BASIC, you had variables, and variables could have names, and there were two possible names. You could either be, so a variable could either be size 1, length 1, let's say perhaps length is better. In which case it had to be a capital letter. Or it could have length 2, and then it had to start with a capital letter, and then the next character was either a capital letter or a digit. So the second character is either cap or digit. Okay. So in other words, this was a variable. You could call a variable A. You could call a variable A1. You could call it also AA, or you could call a variable. But 1 was not allowed to be a variable, obviously, because that would be confusing, right? That could be a number. So these are the 3 types, if you want, of variables that were possible. So now the question is the number of possible variables. Now, if you ever have to write a serious program, you like the fact, I'm sure, that nowadays you can variables, give them long names, because you sometimes need a lot of variables, okay? And so if you were limited, and you'll see we're not that many choices, then... Okay, so how does this work? Let's think about how do you form this. Well, the first thing is, so you have to think of this as a procedure. So the procedure of choosing a variable name. So what are the steps? And then we from that we can well, the first thing is to decide, am I going to give something length 1 or length 2? So I have a choice here. So we choose length 1 or length 2. Okay? And so I'm going to count the number of possibilities of length 1, and I'm going to count the number of possibilities length 2. And what do I do with those? Remember, now we are choosing one single guy, right? One variable. So it either comes from here, it either comes from this collection or from this collection, and therefore it is the sum rule, right? So what we're going to do eventually, I'll put it here in already as, I'm going to add, no, that's not very legible, right? So, okay. Let me put, so I'm going to add these two. Whatever number that I find here and the number that I find here, that is going to be my total number. I'm going to add, this is the sum rule. But now, let's think about what are the possibilities here. How many possibilities of length 1 are there? That's actually very easily answered, right? Because remember, it has to be a capital letter, and we all know that the alphabet has 26 letters, so we had 26. The number of possibilities was 26 here. But length 2, what is happening here? Now we have to build another, the procedure is now a little bit more complicated. You have to do 2 things, right? You have to do the first character and the second character. Okay, you build it in 2 steps. The first step, what do you do? Well, you choose to be, the first choice has to be a capital letter. So how many choices are there here? 26 again. Now the second character could be either a capital letter, 26, or a digit. So how many possibilities are there here? A cap or a digit? Well, so there are 26 capital letters, there are 10 digits. What do? Multiply? No, add again, right? Because it's or. We pick only one of them. So this will mean that there are 36 possibilities here. Now what do I do with this? Well, I have to choose 1 and then I have to choose 2. So I'm building a pair here of 2 characters. So we have to do the product rule. Okay, so this was the total number here will be 26 times 36. Understand that? Okay. So what does that mean? Right. So in total, that would be 26 plus 26 times 36 possibilities. Now there was one other restriction. So there was a third restriction. There are 5 exceptions. Why does it get into a circle? What, can I erase this? Oh. 5 exceptions. There were 5 variable names you couldn't use. I don't know which one they are. I'm sorry, that part I've forgotten, but there were 5 exceptions. So, in other words, out of this number of number here that we had, that's, by the way, let me calculate this number for you, just that we know what we're talking about. So that is 26 plus 26 times 36. That is supposed to be 962. That's all possibilities, but there are 5 exceptions. So where does that go in? Now we are difference, right? We're going to subtract. So sometimes we have to subtract. That means there are certain choices that cannot be counted, and we have to uncount them. So these are the number of possibilities, the number of valid possibilities, meaning what do you have to do? As I said, we have to subtract these 5 from that, and so this gives me no, 957. Yes, 957 possible variables. About 1,000. It was still good enough to write decent programs. Okay. Okay, so here's another, a more difficult one even. Passwords. Now, to keep the numbers a little bit smaller, I'm going to do a bit different than the book. Say, I'm a little bit of concerned about my security, so I'm allowing, let's say, perhaps pins are a bit better than passwords, allowing 4 to 6 strings. Say, allowing length 4 to 6. So. To have length somewhere between 4 to 6. Okay, 4 or 6. Now, what can you do? It has to contain consisting of, let's see, of uppercase letters, of course, I mean, normally what we would say are letters where we don't distinguish between the case. So that sometimes we speak about letters, I mean, doesn't matter whether you're upper or lowercase, but sometimes it's sensitive upper lowercase. But let's say, okay, upper lowercase or digits. Again, we know how many digits there are, okay? But it has to contain at least 1 digit. But each password has to contain at least 1 digit. So this is a restraint. Remember, there was this. It's an example of the basic. We had variables of length 1 or length 2, but there was an exception, if you want. There were 5 exceptions. Here we don't. The number of exceptions is left vague. The exception is it has to have a digit. Okay, or I mean restriction. I should not call it exception here. So how do we solve a problem like that? Well, it is actually really the way that I wrote it a little bit is 2 parts. So part 1 is, let's look at unrestricted possibilities. Well, first of all, perhaps, no, okay. Let me do it this way. It's better to do it in two steps. Well, first, part one is, so remember, I'm kind of, let's think about it as a procedure again. The procedure is I'm going to choose a password. So choose your length. Okay. So there's what are going to be? I can do either a password of length 4, a password of length 5, or a password of length 6. Okay. So again, so I won't choose in one of those. So what we'll do in the end, we're going to add them, right? It's a sum rule, so we add numbers. Okay. So P4, let's think about P4. So unrestricted choices for P4. So without the constraint of the digit, what are the choices? Well, there are 4 characters I have to choose, and I could choose among many. Well, there are uppercase letters, there are 26 uppercase letters, or digits, there are 10 digits. So again, it's an or, so we have to pick one or the other. That means there are 36 choices. So we have 36 choices for the first one, 36 choices for the second, 36 for the third, and 36 for the fourth. Okay, so 36 to the power 4, that is 36. Oh, sorry, I have to open this up now. 36 to the power 4, it's supposedly 1,679,616. Quite a lot of passwords. But this is unrestricted choices. How can I find now the ones that have contain a digit? So you could think, okay, so perhaps I do this thing that is process as building this 4-character password, and then I decide where I'm going to choose the letter, the digit, or where at least one digit. Now there is an easier way, and this is an important thing to realize. This is somehow the hardest part, is to see how to solve this. Okay, what is the strategy to solve this? So one way you could do it, you could think of this as if you have to approve this password. What would you do? Well, you would make a list of invalid passwords. So what's the number of invalid passwords? What is an invalid password? It's a password that does not contain a digit. So in other words, if I had to make an invalid password, what I have to do? For the first choice, I have to pick a letter. I cannot pick a digit because then it becomes a valid one, right? By the way, there's no constraint on the number of digits. I could very well just pick a pin by just taking digits. The only restriction is there has to be at least one digit. So in other words, an invalid password would be if I choose one of the 26 letters here, one of the 26, one of the 26, and one of the 26 here. So, and again, we have to multiply it because it is, each of these are picked independently, and we create something of length 4. So these are the number of invalid passwords. So what is the number of valid passwords then? And here we get again to our subtraction principle, right? If we have a certain amount that is acceptable, possible, and there's a certain amount that has to be rejected, then we have to subtract these two. So, okay, 26, that is 26 to the power 4 is 456,976. Okay, so the number of valid passwords is now going to be the difference. It's going to be this number minus this number. Okay, it's a huge thing, but okay, just for, I'm not going to work out the other details, but just to have an idea of what this would be. So this would be 1,222,640. I might have made a mistake. You have to do the calculation again. So this is P4. So P4 is equal to, and instead of writing the numbers, let's write it down in the formula, because that's what I want you to do. I don't need you to calculate the actual number. I want you to write it down in a compact formula. That's more than enough. So this is 36 to the 4 minus 26 to the 4. Okay. We can go now a little bit quicker. What do you think is P5 going to be? I have to make 5 choices. Okay. Let's just do what are the possible choices when when I'm not looking at the restriction? Unrestricted choices, I have now, instead of 4 choices, 5 of them. So this will be 36 to the power of 5. Okay. Now, what are my restrictions or invalid passwords? The invalid passwords now, instead of 4, I will have 5. Everything that a 5-letter password, that password of length 5 that has only letters in there. So there's 26, 26, 26, 26, and another 26. So that will be 26 to the 5th would be the invalid number, and that's the one that I have to subtract. And then finally, you can hopefully see that this will be 36 to the 6th, 26 to the 6th, right? What this represents is there are 36 to the 6th possible passwords with letters and numbers, but I have to exclude those that have no numbers in them. And that's the total number. And now, what are the total number of all these things? That's adding them up. So the total number is adding this all up. So add this up, whatever this number is. I don't want to know the actual details of that number. Okay. So there's one more rule that I want to quickly go on, and it is the so-called. Let's go back here to the very first example here that I had made. And I'm still, again, going back to this thing, and I changed the menu a little bit, and they added here, in this thing, a cheese platter. But if you're French, you like to eat your cheese as a dessert, so they also put it here, a cheese platter. If you ever go in a fancy restaurant or you go to France, that's what they give you. At the end of the meal, they give you a cheese platter. So what is now the problem? Okay, I'm again choosing, let me get rid of these 2 letters here. I'm again choosing one of each. Sorry, not one of each, one item, either an appetizer or a dessert. So if we would, so we have changed the things now. So let me erase this. Let's get rid of this whole thing. So what are the possible orders here? Well, there are 5 appetizers that I can choose from, and there are 1, 2, 3, 4, 5, 6 desserts. So you say 11. There are 11 possibilities. Do you agree with me or not? No, because what is going on? Suppose I have chosen, I say I'm going to take an appetizer, and as appetizer I choose the cheese platter. Now, another version of me in an alternative reality on Earth 39, 32, where is, I forget now where Kara is, it's 38, 36, 38. Okay, on that Earth, I choose a dessert. But I'm a cheesy person, sorry for the pun, I'm going to choose the cheese platter again. So, in both cases, I did presumably something different, but I ended up with the same. So, in other words, what happens here, there is an overcount. These two are this is a choice that is in both of these possibilities. So I counted this twice, and I should not have counted this twice. So what I should have done is therefore, so let me correct this. What I should have done is subtracted the double choice. I picked cheese platter, I could have chosen it twice, so I have to subtract it once. And so the total possibilities are 10. So what does this mean in terms of sets? So again, let's call this A1 and this A2. So what is the cardinality? We said an sum rule corresponds to an OR, right? We're choosing one or the other. But that's the problem now. It's no longer exclusive OR because there is something in common. So what is the size of these two things? What this means that in common is that means that A1 and A2 are not disjoint. Remember, I had put this at some point. Let me see whether I can still find this when I had wrote down the formula. Here, right? I said this is the rule for the size of in this case, a union of 3 sets, but okay, you're flexible, right? With 5 sets, it would be the sum of the 5 and so on. So, but they had to be disjoint. Now, it's not the case. And what happens then? Well, it is the number of elements in the one set, the number of elements in the second set, but now we have counted some numbers twice, namely the ones that are, so if I represent A1 and A2 here in a Venn diagram, so what I counted this, that perhaps I color this. A1, this counts exactly the red ones, okay? No, let's do green. A2, that sounds the green ones, okay? But you see that everything that is in here, and disjoint means there are some things in there, is counted as a red thing as well as a green thing. So I have to subtract it once, and that means the size of the intersection of the set. This is the main rule for 2 sets, whether they are disjoint or not. By the way, if they are disjoint, then this last term here, of course, is 0, so it's still the same formula as before. So this is called the exclusion-inclusion principle. Let's see. Inclusion-exclusion. Yeah, sometimes people say the one thing, the order is they say inclusion-exclusion principle. Okay, and that is very important, right? That when we have, when there's a procedure and we can do either one way, and there's several choices in the first way and there's several choices in the second way, but there are choices in common, and those we have to then subtract in the sum rule. So an example here is, for instance, let's do one problem. You'll see, it can get quite complicated. Suppose, how many number of strings, bit strings, of length 8 start with 1 or end in 0, 0. Okay, so imagine that I'm calling these special bit strings. They're bit strings that code something. Let's say me and my friends, we have a coding system, like a secret key system, and we say you only have to look at bit strings that start with a 1 or end in 2 zeros. The others you can ignore; they're just noise. Okay. So, but how many are there? Okay, let's think about this. So, first of all, how many bit strings of length 8 are there? So, step 1. Yeah, sorry. In the first, I was doing part 1 and I never got to part 2. Well, of course I did, but I didn't mention they were. So, step 1 is the number of bit strings of length 8. Let's start with that. That's 2 to the 8. I hope that's something that we have now all seen, right? It's 2 to the 8. Okay. So that is perhaps not a necessary thing that we need, but it's good to have to know this. So perhaps I'll call this step 0. I'm not gonna. Let's not make it into steps. Okay. Just information gathering. Well, let's now look at all these. The 2 valid strings. So the strings that start with 1. How many are there? So the number of strings that start with a 1. Well, it's a 1, and then we have 1, 2, 3, 4, 5, 6, 7 choices, and whatever I can put there. Okay? So I have 2 choices here, 2 there, 2 there, 2 there, 2 there, 2 there, 2 there. So the total number is 2 to the power 7. Right? Because all these choices are now independent. I can choose whatever I want. Zeros, I can choose everything 0, everything 1, or whatever pattern I like. Okay? That's the number of strings that start with 1. What are the number of strings? And try to answer this already before listening to my solution. Remember, this is something where you often should stop and say, well, let me see what I can figure this out before he says it. Okay, so what is this now? Well, they have to end in 0, 0, and then how many left? 6 more choices left, right? And each of these choices again are independently 2, 2, 2. Okay, so it is how many? 2 to the 6th. So what do we do with these numbers? It's an or. Should we add them then? Right? It's this or that. Well, yes, it's this or that, but for instance, let's look at this one. 2, 4, 6, 8. This string here. That's a string that I could have built. So I could either have decided I'm going to build a string that starts with 1, and that would, so it's one of these 2 to the 7 possibilities. That is this guy, right? So it belongs to this collection. But I could also have built a string by saying, okay, the last 2 are zeros, and now I choose the 6 other digits. So that would have meant choosing these 6 here, right? So what does it now mean? This it also belongs to there. So we have a common element. So this is A1, this is A2. So what we want to calculate is how many strings are there of either this type or that type. Sorry, I have to be careful with the English word either. How many strings are there of this type or this type? Not exclusive or. Okay, that's the whole point. The inclusion-exclusion principle says it's the number of bit strings of the first type plus the number of bit strings of the second type, but now subtract the number of bit strings that you have counted twice that way. So we need to calculate this here. So what does that look like? So these are the number of strings that we have to calculate that start. I said start with 0. I meant end with 0 here. So I did it right, but I wrote it wrong, right? So that start with 1, end with 0. Well, let's look how they look like. Well, they look at 1, and then I have 5 possibilities, and then 0, 0. Right? 5 spots. If I want to build a string that starts with a 1 and ends with a 0, well, I have to start from this, and now I can make my choices. What are my choices? 2 for this, 2 for that, 2 for that, 2 for that, 2 for that. And we multiply because they are all independent choices. That is 2 to the 5th. So, what does this now tell me? Well, there were 2 to the 7 strings that started with a 1. Okay? This is what I said here. There are 2 to the 6 that ends with a 0. Okay, so that's 2 to the 6th. What is going on here? 2 to the 6th. And then there are the ones that start with a 1 and end in a 0. That's these guys, and there were 2 to the 5th. And those I have to subtract. So this plus this minus 2 to the 5th. Okay. So if you would work this out, 2 to the 7 is 128 plus 64 minus 32, so that turns out to be 160. Okay, so this is an example where you basically use everything a little bit, right? Because the product rule we use all the time here, by the way, right? This is each time use of the product rule. This is each time the use of the product. This is a product rule each time, right? Each time I'm saying, I'm sorry, there's something, my thing is getting out of juice here. Okay, and this is each time I use the product rule, and then I use the sum rule, but in its more full form, in its inclusion-exclusion principle that I have here. Now the inclusion-exclusion principle, sorry for that, if you have more than 2, it gets a little bit trickier, and I'm gonna leave it for that. Now there's one more rule that I have to discuss, and that is the division rule, and that says now, okay, I'm gonna leave this for you a little bit. I'm gonna do one example and then explain where it comes from. Okay. Suppose I have a table and I have to seat 4 people. So seating of people A, B, C, and D. But a table seating is considered the same if you have the same neighbors, right? If you can turn the table around as long as everybody is sitting next to the same person, that is considered the same seating. In other words, what I mean to say is, so what are some possible choices here? There's something not working properly. Let me get rid of this. Sorry, I don't know why. Give me a sec. Sometimes I have to. pen dirt, or something happened with my pen. Oh, I see. It was screwed off. Okay, so we could have put A here, B, C, D, but this is considered the same seating because A sits next to B on his left. This is B, and on his right is D, and that's the same for everybody. Has the same person on his right, so they are considered same seating. These two. So what are the numbers of seatings now? Let's think about it. Well, let's call these first different. So the number of seatings, number of absolute seatings. In other words, it matters whether you're sitting north or south or east or west. Okay. Well, what are the choices? Let's see. I have to put a person. How many choices I have to put here? 4 choices. Now be careful. How many choices I have to put here? I cannot put the same person there. That's not possible, right? You cannot split a person in 2. So there's only 3 choices left here. And for this, the next spot I want to fill, there are 2 choices. And then finally, of course, there's only 1 choice. So in total, there's 4 times 3 times 2, that is 12, is 24 different table arrangements if north and south and east matter. But they don't. So what are the number of seatings, table seatings? So in the setting, in the meaning that they can be considered the same if you can rotate them, so to speak. Well, that's the whole point, right? There are, now I can just say, okay, wherever is my person A, let's take, I don't know which one is person A, but I can always turn my table around that person A faces north. Okay? So, in other words, what are the 4 possibilities for A? He can sit in the northern spot, in the southern spot, in the eastern and the western spot. Okay? So, of the 24 possibilities, there are 24 different possibilities. But each group of 4 are the same. Namely, I can move, if A sits in the east, then I'm rotated 90 degrees. So if A would be sitting here, I just move the table, like in this case, I just turn the table one way in that direction, and I get this table seating. Okay? So each case, there are 4, each of these absolute seatings, they are considered the same. And so this is so-called the division rule. So we divide by 4 here, because of the 24, they are grouped in groups of 4, which considered being the same seating. We identify those 4 as being the same. So this is therefore 24 of the 4 is 6. So I'll stop here. There will be a homework problem on that. It's going to be a little bit. We were going to use it also, but especially most of the homework problems are on these previous counting principles that I just discussed.